All right, welcome everyone. Today we have Brandon Allen talking to us from North Dakota State University. And before he gets started, I'd like to remind us of the community statement for GOCC. The first part is that we're all learning. And so this is a friendly learning seminar where we get to learn from one another. And the second part is that everyone has something to contribute. So we're all on different parts of our journeys and our mathematical adventures. So feel free to contribute your knowledge if you have some, or ask questions. And also the last part is that no one has all the answers, but if you run across any questions during the talk today, feel free to put them in the chat, or you can also unmute yourself and ask directly. If you put them in the chat, one of us organizers will probably ask the question for you if you are not able to ask it yourself out loud. But yes, with that said, let's all welcome Brandon, and he's going to be talking to us about chromatic polynomials of Coxeter groups through the Brink-Howlett automaton. So welcome, Brandon, and go ahead.
So my talk is going to concern the Brink-Howlett automaton. If you haven't heard about the Brink-Howlett automaton, it's probably reasonable assuming so, because it's been inside the University of Sydney, New South Wales for about 30 years and has only grown in fruition there. Papers are produced out about once every 3 to 4 years. Started out in the 90s with a PhD student with the last name Brink and her advisor, Brink-Howlett. And it was in her PhD thesis that the automaton was constructed. We'll get to that point later on in the talk. But the thing is we need to focus on, first off, what has been done with chromatic polynomials. And we'll go over a little bit about that. My research has been in development for about 3 years now. A lot of this talk is already known knowledge, but basically I added my new twist, in which synthetically combines a lot of things from combinatorics, and then I compute out chromatic polynomials. Okay. So first off, I'd like to acknowledge the University of Sydney, New South Wales, for cultivating automaton. It's not something that's very simple at all. It's something that looks grotesque, but once you apply it, things turn out nice. And the Brink automaton was used mostly for calculating out words of length n for Coxeter groups. So the word problem, if you're knowing of that in algebra, directly related to the Brink-Howlett automaton. Also, like to thank Federico Ardila, and he has his whole algebraic combinatorics lecture series online on his webpage. I cannot recommend it enough. If you're into algebraic combinatorics, go there. It's very nice. Lectures, homeworks, and all. And also my math department for giving me the time and space to work on it and reviewing things with me and listening to talks and things like that. This is the first talk in which I'm going to go over things with an outside general audience. So I'm pretty ecstatic and I'm pretty happy to do this, to get outside the walls of the university. So the goals of this talk is to calculate chromatic polynomials. We'll label that chi of WS, where W is the group and S set generators for types AN-1 to DN. This has already been done by Stanley, but we'll review it because it gives us inspiration for what we do. And then the second point is new. Well, give a systematic way to calculate chromatic polynomials for types. The affine group on 2 generators and the affine symmetric group. Okay. And so the classical way of thinking about chromatic polynomials is that we think about them in like hyperplane arrangements first, which is seeming odd, right? So whenever you thought about like a chromatic polynomial, they counted the proper colorability of some graph. That's what you were taught in like some undergraduate combinatorics course. But in all actuality, like you can do the same with hyperplane arrangements, and I'll show that later on. Why that's the case with like a 4-line proof. It's not hard. So you do a hyperplane arrangement, and we go in the way of Stanley, and Stanley has a whole PDF document for hyperplane arrangement theory. And so, right, you have your set of hyperplanes and RD. These HIs, right, are vectors and RD, and it has a BI equal to 0. We'll always just assume BI is equal to 0 in our talk. Sufficient. We don't need BI to shift. Okay. For example, right, in R2, our hyperplanes are lines. In R3, our hyperplanes are planes. If you need that, for example. So example, with a Coxeter group, AN minus 1, SN, n greater than 3, it's defined by the hyperplane arrangement. So you set xi equals to xj, where your coordinates of I and j vary but not equal to one another. And then you see a one-to-one bijection, one-to-one correspondence, sorry, with the regions of AN minus 1 to permutations of SN. And just like in the last talk, right, you start with a base element E1, 2, 3, and basically what these hyperplanes do is that they swap the coordinates, right? So if you want to swap 1 and 2 here, you go over the line 1 and 2, and it swaps the element 1 and 2 in the first and second position. You get 2, 1, 3. And you go around here and you get the permutations of S3, right? And so a nice thing, if you've done a lot of algebraic combinatorics, is that you'll see that the regions of A of n minus 1 is actually n factorial, right? And we'll get to that a little bit later in the talk. And it's just a special property of the chromatic polynomial. Okay. And so we're going to need another definition. Okay. See, it's like a gallery of like combinatorics that you're seeing. Here's an intersection coset, LA, and you take your elements as the intersection of your hyperplanes, and your order and reverse inclusion. So here's an example of that. You got your hyperplanes on the left, 1, 2, 3, 4 labeled nicely for you. And then you got your last of flats on the right. So starting at the bottom, you have the empty flat, so the empty set. And then you do for each flat, each hyperplane, sorry, 1, 2, 3, 4. And those are all linearly independent in and in themselves. Then what you get with that 1, 2, 3 is that you see that when I intersect 1 and 3, right, I get a 2-dimensional vector space. And then 3 is just a summand. I mean, 2 is just a summand of 1 and 3. So you get 1, 2, 3, and then you do the rest for all the rest. So you get 1, 4, 2, 4, 3, 4, and those are all dimension 2, right? So there's a little sense of matroid theory in here, which I'll not go over, but you can see in our Dildes lectures, took the example right from them, okay? And then you intersect the rest for dimension 3. So you get 1, 2, 3, 4 on the top, okay? It's pretty standard, okay? So now that we have elastic flats, we can construct a Mobius function. So we all know our good old Mobius function, right? So we start with 1 at the bottom, and we alternate summing based on the vertex we're at. So at the bottom, we're at 1, right? Because 1 if x is minimum. And then we're going to have negative 1s on top, because when I start at, let's say, the leftmost vertex on the second row here, I'm going to have only 1 on the bottom. So I sum that and I take the negative sign. So then I get negative 1, negative 1, negative 1, negative 1 for each one. And then I move up to the third row here. So with the leftmost vertex, I get what? Well, I look at all the vertices below and I sum those together. So negative 1 plus negative 1 plus negative 1 equals negative 3 plus 1 equals -2, and then I reverse the sign, so I just get 2. And I do that for the rest on top here, and you'll get 1, 1, 1. Doing on top here, you're just going to sum all the rows together and reverse the sign. So then you get what? You get -2, right? Good. Okay, good. View from combinatorics class. It's all good, I think. So there are some theorems that I'm not going to state here, but I'm going to be very cheeky. And I'm just going to define this chromatic polynomial here as taking the lattice of flats and then looking at the dimension and looking at the Mobius function as the coefficient. So the Mobius of flats here just basically states, well, I'm going to align all my numbers on the right-hand side. So this -2, 5, -4, 1, when I add up all the rows here. And then I just take it as its polynomial going from bottom up, where the bottom corresponds to the highest degree in my polynomial, right? All right, good. And if I plug in q equals to -1 here, Zeskaleski in 63 or 65, I do believe, this will calculate out the number of regions in my hyperplane arrangement. If you plug in -1, you're going to get 12. And so scrolling back up here, you see here, this is just 1/4 of the upper plane in 3 space. So we have 12 different regions when you reflect this. So there's going to be an empty region next to 1 and 3 that doesn't have this hyperplane 2 in it, but there's going to be a back corner one that does, and thus you'll get 12. All right, good. So, right, we can calculate out a nice way of calculating out hyperplane arrangement chromatic polynomials is just using deletion and contraction, right? So deletion, you just delete a hyperplane. In contraction, you just project all the hyperplanes pretty much onto one. So if you need an example here, we'll scroll back up again. Say we want to project down onto 4, well, then you're just going to have the hyperplane arrangement of, right, maybe I can do this. So here's 4. And then you can have 1, 2, 3, right? So here's 1, here's 2, here's 3, okay? So that's what contraction does. It's not a very, very obvious property, but it's used when you're doing graphs as well, and we'll see the correspondence. So for a hyperplane arrangement in the finite space FQN, then you can take the chromatic polynomial equaling to your points in your field, the nth degree. So it's an it's an f times f times f n times field of q numbers, and minus the hyperplane arrangements. And that will give you your chromatic polynomial. Once again, I am skirting through theorems, okay?
A quick question.
Yeah.
So contraction for a chromatic polynomial looks really nice in the lattice of flats, right? Because it's just your interval from that hyperplane up to the top, I want to say. Like it's your order ideal of your hyperplane.
I haven't thought about it that way.
Okay. Because
I don't really think much about order ideals. I use it as one theorem to propel myself in Bajor and Brenti.
yeah, I guess.
But I think so.
Filter would be the Stanley term, but yeah, just it's because you're just looking at everything that intersects your hyperplane and your lattice of flats, like the things that intersect a hyperplane should be everything above it in the lattice of flats.
Yeah.
Okay.
Yeah.
Sure.
I just use a matrix theory definition, but I don't state it because it's really complicated. Then you have to go through the weeds. So yes, okay, good. So a really nice thing that combinatorics have produced out is something called the finite field method, okay? And this finite field method saves you a lot of headache about constructing this lattice of flats from, you know, like some hyperplane arrangement. This lattice of flats could be like huge, and it's really like mind-numbing, and you don't really want to do that sometimes. So the finite field method helps you out of that. So you let your chromatic polynomial of a hyperplane arrangement be the number of points in f of q to the n that are not on any hyperplane of AQ, where AQ has integer equations and in for Q a large enough prime. Okay, we need Q to be a large enough prime sometimes, because else we're going to lose information of our hyperplane arrangement. So here's an example of that. It's a pretty nice drawn out example. So you got x equals 0, y equals 0, x equals y, x plus y equal 1 with q equals 5. Then you'll get this hyperplane arrangement in FQ2 where q equals 5. And you see here that, well, we start off with q squared points for the total lattice. And then by inclusion exclusion, we're going to take minus q for each one of these hyperplane arrangements. And then we add in 1 because we've minused this one out twice. And this one out twice. This one out twice. Add this in double time. So you minus that out 3 times by principle of inclusion exclusion. Right? Nice gallery of combinatorics. That's all I'm doing. Okay. All right. Now here's where we get into some little fun stuff with Coxeter theory. Okay. I think we have a question, maybe. Looks like a missile getting launched. Okay, sounds good. So we denote our vector space as v equals r to the n, and you do the standard basis. So you let e to the I equals 0 for all entries except for the ith entry, which is 1. And you let ei, ej, that bilinear form, be the Kronecker delta. So I equals j, it equals to 1. Okay. And it's well known that Coxeter groups through V to GLN V are going to have the corresponding root systems for type AN through DN. Okay. And that Q component plays a big part with this, sorry about that, with this plus or minus 2 EI. And that's kind of like why we need like Q to be a high enough prime. Okay. So right, when we do the finite field method, which is an exercise in Stanley, which I'm providing for you really nicely, right, you can choose Q elements to be the first coordinate, right? So Q elements for the first coordinate, right? Q minus 1 elements for x sub 2, right? And this is x sub 3, right? This is x sub n when you do that all out. And by Zescalesky's theorem, when you plug in -1, you get n factorial. How convenient, how nice, right? And we can do the same thing for type P of n. So, right, this is the condition. Since xi cannot be 0, it has to be q minus 1 for x sub 1, q minus 3 for x sub 2, because it can't be 0, and it can't be the same as x sub 1. And you keep on doing that, plug in -1, you get 2n times n factorial. Okay. And you do the same for c of n. So, right, 2xi cannot equal 0. And then you get what? Q minus 1 elements for the first, Q minus 3 for the second, on and on, and you'll get the same number of regions. Okay, so it may not turn out that your regions are unique. B and CN show that through the chromatic polynomial. Yep, and you have probably done these exercises before because they're in a Stanley, but they motivate my research because we have to look at the hyperplane arrangements later on. Okay, and here's type Dn. Okay, you split it up into two different ones, one with a 0 and one with not, and you plug in -1, you get 2n minus 1 times that. Okay, good. Okay, so now we have all of them for AN through DN. So here's the proof of hyperplane arrangements are just the same as proper colorability of a graph. Okay, so you take a hyperplane arrangement and there are going to be number of points on no hyperplane, xi equal to xj. That's equal to the number of ways to color the vertices of G with Q colors so that no two neighbors get the same color. And that's equal to the chromatic polynomial of the graph G, which is chi of G. So hyperplane arrangements are the same as graphs. Okay, and you can interchange the two, which is really nice, right? So I use this as a springboard a bit. I don't want to go too much into details about the historical way that I've conjured up chromatic polynomials for affine symmetric groups and affine irreducible Coxeter groups. So, right, we have the types for A and to D, and so how about the other finite irreducible Coxeter groups? They also have vector representations. Sage could probably just compute those out for you for like type E6, E7, E8 if you need to. So what I don't see a lot in like text is like calculating out for affine irreducible Coxeter groups, and they don't really list that as an exercise or anything. Like nobody really studies it. They just like pick the first 4 finite ones, and since they have nice closed forms, like it's all good. It's all shady, right? Because what we've seen before is that our chromatic polynomials are just in closed form with n, right? So can we do the same for the rest of them? So you can, it'll go through the Lie algebra route, and you'll look at their corresponding geometry by something called the Shefili symbol. But my question is like, I'm an algebraic combinatorialist, so I want to know like, can you do it combinatorially? Like, how close can you get combinatorially to it? I don't know, like, it could be close, it could be the same exact thing, it may be far off, like, let's see. So, for Coxeter groups, right, from last talk, here is a standard definition of what a Coxeter group is. Mij is just the order between two generators. Hopefully I just don't have to go over this, and just you can look at the last talk if need be. In Bajor and Brenty too. A lot of things that I'm going to take from now on are from Bajor and Brenty. Yika Yao's thesis, Yika Yao's work at University of Sydney, New South Wales, with his advisor, Parkinson, if need be. Okay. All right. So here's how you construct a Coxeter diagram, or what they call a Lincoln diagram, right? So when you take two generators and look at their order, right, you have a vertex S, that's your generator, and not connected by an edge is 2, connected by an edge is 3, connected by a line with weight label is greater than or equal to 4, and they'll be represented on the graph. And you see that a Coxeter system is in 1-to-1 correspondence to a Coxeter diagram. Okay, and let's just go over an example of that, right? So if I just label these as S1, S2, and S3, and this is S1, S2, S3, right? Along the diagonal is just going to be 1. S1 and S3 are not connected, so you're going to have a 2 in the upper right corner, in the lower left corner. And then since S1 and S2 are connected, place a 3. And since this has an edge label, we can put 5 for S3, 2 and S2, 3. And also, our edge labels, by our definition, could have infinity. So that means that the relation between the two generators is free. So you could go S1, S2, S1, S2 on infinite, and it doesn't like close down or collapse. All right, so here's a geometric interpretation of A1 tilde is just the paragon or the long line on the plane space. And basically, right, we can have a start node E, right? And then we can go S, T, S, T, and do that on forever. Or we could do T, S, T, S, and go on forever that way as well, right? And we can color this thing, right, with just 2 colors, okay? So we just alternate red, blue, red, blue, red, blue, and then this is red, then it's blue, red, blue, red, blue, red, right? But the weird thing is that when I try and color this, right, I am not going to have some polynomial when I just take like this form here, right? Because my degrees on Q, right, is going to be infinite, and then you're going to have a Q minus 1 here, right? That's also infinite degree. So what mathematicians have done is basically they just take something called a region, and then they just say tessellate it. So I can just get these out and just tessellate through. So it's Q times Q minus 1 for its chromatic polynomial. All right. So this is the old way of thinking about it. Okay. My polynomials are not going to be this, but they're going to have close resemblance to it. And I'm going to notate it that way so that we are very precise, because we don't want 2 same definitions together, and that'd be bad. Okay. But this is the old way to think about it. Just take a region, tessellate it. That's all good. And here's a more trickier example, right? They take a fundamental region of this and just say tessellate, yo. That'd be great. So doing that, right, you're going to get 2 colorability. But it seems like infinity, the moral of the story is going to be like infinity does weird things to your chromatic polynomials. It doesn't like to play with the chromatic polynomial nicely. You kind of have to force it. So to build a chromatic polynomial of A and tilde, so we're going to turn the affine irreducible Coxeter group into a finite digraph in its minimal form. I won't talk about a lot about minimality, but I have resources if you need discussions about minimality. Those come from Parkinson and Yao over their research for the past 5 years. And then you put the digraph into a graph just by removing arrows. That part may seem strange because we know from combinatorics point of view, like graphs are different than digraphs. The chromatic polynomial is going to be a little bit different, but I'll give an argument like how I can exchange the 2. And it'll do with walking through the geometric configuration, applying dots and going over the hyperplane, essentially. And then you calculate out the chromatic polynomial of the graph to obtain a chromatic polynomial for affine irreducible Coxeter group. So if you need one slide about like how I'm going to do this, like this is what to take away from the talk. So form into a finite digraph, remove the digraph arrows, calculate out the chromatic polynomial. Okay. So if I just gave you that long line with A1 tilde, you could probably like generate this, right, by yourself, right? Give you 10 minutes. I say, give me the digraph of A1 tilde. And you could probably give this to me in 10 minutes. right? So it goes starting at the empty word, right? Then you have A, B, and then it just transitions to A, B, A, B, A, B, or B, A, B, A, B, A, whatever length you want, right? And you can get the chromatic polynomial, right? By just saying, well, I can color this node by Q colors, this node by Q minus 1 colors, this node by Q minus 2 colors. Why? Because, well, it can't be Q because it shares a neighbor with the start node, and it can't be Q minus 1 because it shares neighbor with alpha 1. Okay, and those alpha 1s and alpha 2s are actually going to be really important later down the road. So, right, I label my edges. Okay. Now, that's not really like the chromatic polynomial for A1 tilde, right? But we could say, well, it is 3 colorable, right? Because if it's 2 colorable, it has to be 3 colorable, right? Just alternate it, right? Like that's all I'm doing is that I'm creating a maximum for the proper colorability of my affine Coxeter group. It may not be the minimal one, but it can be at least a maximum, which is fine. It's not the best, but it's best right now what we got in combinatorics land, right? Without going through the Lie algebra. So here's a definition of Reposit, which you'll find in Bajor and Brenti, right? So you got simple roots, alpha 1 through alpha 2, and those just correspond to our generators S sub 1 through S sub n. So every generator is associated with a simple root. And then you take V, a finite dimensional R vector space equipped with a symmetric bilinear form. This is also in Bajor and Brenti. I won't go over the construction about that. But you take negative cosine, pi over mij, and we treat infinity, so pi over infinity, like it's 0. Okay, I won't go over the proof of that. Find that in Bajor and Brenti. Okay, so you recall that alpha is positive if you can represent it as a positive linear independent set, and for all ci greater than or equal to 0, and negative if for all ci is greater less than or equal to 0. And then you can construct a root system. So basically, when you have if you have a root, you can slap on a generator to it, and then you can calculate out what the next root would be. So it may not be a simple root, but it's going to be at least a root. Okay. And basically, all your roots are just form of words from your Coxeter group in simple roots. Okay. And also, your roots will always be positive or negative. It will never be a mixable. And that's always in Bajor and Brenti as well, if need be. That's a pretty classical theorem. Okay. So here are some post sets. So on the left, you have A3, and on the left, you have the affine group of 2. So you get a finite one for A3, but for A tilde 2, you'll get an infinite root post set. Okay, and that's not finite, right? You're like, why are you talking about these root things? Like, it's not finite. But it'll pertain easier, okay? Because we're going to create another classification of roots, which will give us finiteness. Okay, so in order to construct a finite state automaton, we take a subset of the positive roots of W. So the small roots are denoted sigma as the following subset of the positive roots. You have
We have a question.
Roots. Oh, yeah.
We have a question in the chat. It's reduced expressions. Are those the same
Yes.
thing as walks in this diagram?
Brink-Howlett automatons recognize the reduced words of the Coxeter group. Yes. Even when it may not be in minimal form. Okay, good. Yes. Yep. So, right, you have your simple roots. So all these alpha S's, and then the special condition on the bilinear form s be between -1 and 0. Then when I attach my generator to my root, it's going to be in the simple roots, in the small roots, sorry. And the nice thing about a tilde 2, as we saw in the previous example, is that it just has these roots here. So alpha 1, alpha 2, alpha 1 plus 2, alpha 2 plus 3, alpha 1 plus 3. Because, as I denoted in my example here with these red lines, these mean that the roots cannot be simple. They have a jump of 2 when you do out the calculation with our lemma here. Okay. All right. So the nice thing about small roots is that they're the cardinality of them is always going to be finite, and you can find the proof in Bajor and Brinty, but it's highly technical, but it's a very celebrated theorem because it will give us a finite amount in which we can construct an automaton, which is good, right? Because we want finite state, which is good. All right. So, right, this is in Yao's thesis, his undergraduate thesis, probably in Brink-Howlett's Brink's PhD thesis as well. That this is the algorithm in which we use to construct our automaton. So you find a set of small roots, sigma of W, using the definition of sigma, so small roots. Then you let T equal descent set of W, and I'll define what that is in the next slide. Things didn't want to fit properly nicely. We can construct ABH iteratively. So you initialize your algorithm saying D, your small descents equal D, which is in T. Then for each S that's not in D, for your root, you put an S label directed edge, where you take alpha S union your generator that you're going to hit the D set with, intersect the small roots. Then you're going to have that as an element of T when alpha S is not an element of T. And we'll see through example, because that's a little bit confusing. So probably example is best, right? And you repeat the step until it stops, and it will stop. That's been proven. Because you have a finite amount, right? You have a finite amount of small roots, so that's all you can do. Okay. Here is A1 tilde. So right here is the direct scheme about how things are calculated out. So since the order between A and B is infinity, right? This implies that you have alpha A, alpha B equal to -1. Since they're small roots, simple roots, sorry, then right, when I hit this alpha B with A, you're going to get this here, and that's not a small root. Okay, and you just go through the definition of the lemma that I gave you previous slides. Do the same thing. See, that's not a small root, so you get your small roots being alpha S and alpha B. Then you determine your small descent sets. So this is the definition of your small descent sets. So you take a root in your small root, and then you hit it with a word, and it's supposed to be less than 0. Okay, so you begin at the identity, and the start node is given by, right, the empty set, right, and we go up where we hit with A, right, and we hit with B, and we have alpha A, right, and alpha B. And then once we have that calculated out, which is alpha A, alpha B as a set, then using those descent sets, you calculate out the new descent sets. However, when you hit B with A or A with B, you're going to end up in the opposite one. Right. And look at what we just constructed. We constructed the automaton that I showed you in hindsight for A1 tilde, right? So good, right? So you get this. Oh, good, like we constructed the same exact thing, great. So there's a determinant formula if you need to calculate out the words of reduced length n. That's in the facts of Bajor and Brenti if need be, but you can just count them through the diagraph here, right? And then Yao, in his 2016 undergraduate thesis, came up with this automaton for the affine group on 2, so A2. So the basic rule of thumb here is that I'm not going to show the automaton calculations of affine symmetric group of 2 because it turns out to be 2 pages long. I'm not going to bore you. I'm just going to say, you can find it there. Here's the diagraph of it. You're all good. Okay. If you need calculations, good. I'm also not going to show the calculation of this. This is just using the graphical arrangement idea that I showed before to calculate this out. And that takes about a page. Listing those down, just calculate. Okay, so notice again, right? Even though it's color 2, this says 4, but you can do the same exact argument. Same, well, you can color with 4 as well. Properly colorable with 4. Nothing stopping you from coloring with 4. Just good. But it doesn't give you your minimal, right? Of proper colorability. So that's a little problem, but it doesn't stop the colorability of what your geometric representation being for proper colorability. It just seems like infinity is really like messing with things up top when you're doing all the calculations of things. So I didn't really mention, I mentioned I can remove my digraph arrows and just remove them. Why? Well, they're just walks inside here. So right, E, S, T, U. And basically when I go over a hyperplane, it's just a line, right? And then each one of these can be just represented by a vertex. And then I can just use the same argument as Lie algebra is and say, well, I'm just going to tessellate this whole thing when I have everything connected as the diagraph shows here, and just tessellate. And so, right, current research is I'm trying to improve this upper bound, and it's not going so well. So the properability Coxeter groups, can we do better than this? Just with the automaton? And I thought about it because what we have here, I think we could, but basically, what happens is that, well, I'll show with an example of A1 tilde. So yes, taking the closure of the union of vertices seems like being the way to go, because what do the vertices encapsulate? They encapsulate vector arrangements in Rn, right? So those are your good old standard, can be represented by some hyperplane arrangement, right? And when I take a closure, I'm just going to connect every vector to an origin point. So for example, with this one, with A1 tilde, you had the empty set, alpha 1 and alpha 2. So, right, when I take the closure, I'm just going to have alpha 1. It's one vector, and alpha 2 as another. Sorry about my writing, hand cramp. So, right, yes, to erase this to make it more apparent. Okay, good. This is alpha 2, right? And doing this will give you this vector configuration. When you go through the lattice of flats, so the lattice is going to look like, right, you got your empty, right? Then you got 1, 2, and then 1, 2. and right, calculating out the chromatic polynomial of this thing, you're going to get the formal expression here. So it seems to do it, but doesn't exclude like the trivial proper colorability of calling it a 0, right? Because that can happen. And when I plug in -1 by Zescalesi's theorem, I'm going to get 0. And that just geometrically, I think, just tells me that you can't have it connected at origin here. Why? Because when I look at A1 tilde, it's basically separating out my space through hyperplanes like this, and it has infinite amount of regions. But even with the polynomial, which I stated was q times q minus 1, when I plug in -1, I still get 2. So it doesn't really represent the number of regions for the whole space. It just represents the region for the slice of space that I took up. So that's where I leave it at. That's currently ongoing. Not much known with taking the vectors in the vertices. Okay. So here's some further study things that people are looking into. At least I'm looking into the first 3. And then these are the ones concerning like Brink-Howlett automaton. These ones for the next 2 are more known generally in Coxeter theory. So for words of like length n for the affine symmetric group, we don't know a closed form for calculating out that. We know how to like synthetically construct, we know how to calculate out their polynomials, we know that they're rational, but we don't know a closed form when you just plug in n, just like with S of n, D of n, any of those. Because those are easily calculatable, but affine symmetric group may not be. So if you're worried about minimality, the affine group C2 does not have minimal automaton. So we can we figure out a small root set where the automation is minimal for every Coxeter group. And that's still an open problem. We don't know. This is an open problem. The co-product of automatons for A and tilde, we don't know. So yeah, I think that's it. Thank you. Get everybody out on time. Good.
Thank you, Brandon.
Yes. So I'd
Right.
like to state that everything up to pretty much like the automaton states are pretty well known. The colorability aspect, I just add in my own. But it's taken some time to really like conjure up like, why can I remove the edges to be not arrows, and we can just have just regular edges instead. Because I was going through some archaic things like polynomials and doing all that jazz, and just like, well, just walk through the graph and just test how Lie algebraists do it. So yeah, okay. Anybody have any questions?
I have a question. Something on your last slide caught my eye. So you talk about the co-product of automatons. That implies that there's a product of automatons.
Yeah.
Can you describe what the product of automatons are?
I think I haven't seen this for like 2 years. I haven't really concerned myself with it because the problem that I've been working on has been like so difficult with like examples, right? Because what I do is like I have to justify like colorability of digraphs, and that's not like superiorly obvious. So I haven't really thought about it, but I think if you just look in Aguila's paper, I think you could trace it back. I'm sorry,
Yeah.
I just list some open problems because our field is very small about the number of people. But these next to last two are very well known in Coxeter theory.
Yeah, so I have a question as well. Is what makes this hard just the difficulty in computing examples?
Computing examples, yes.
Mhm.
Because it goes 1 plus the H box number or Cox box number to the rank of your RIP system.
Mhm.
So that just exponentially, it just gets harder to produce out examples. But right, the geometric motivation, we have those examples calculated out for us. So we can use those as like inspiration for us to calculate out chromatic polynomials through our automaton scheme. And it'll still produce out what you want for colorability, even though it may not be a lesser color number of colors. So it's hard, it gets harder. A3 tilde is just, it's a beast to put on a screen, like no. So that's why I just stuck with the simple ones. People haven't done these. That's pretty good for master's work, I do believe. Generalization can be a PhD. Okay.
I have a pretty basic question. I think I just missed the definition at the beginning. I just want to make sure I understand, because I think I'm going to see this a lot. What is the difference between having the tilde on top and not having the tilde on top? No, it's like an infinite versus finite thing, but.
So let me draw it on this thing screen, okay? So with AN tilde, I didn't really go over like, this is what AN tilde is, and like going through a whole 2 pages of diatribe, but basically it has endnotes, right? And they're all connected in a cycle. This is 1, 2, 3, n minus 1. And this is n, okay? And AN,
Yeah, AN's just in a line of
Just
n
a line,
minus
right?
1, right? Yeah.
It's just a line, right?
Okay. So
Yeah.
in general, is the tilde like you add one more node that's attached to the ends of the line or something?
So for Baki, so the Coxeter groups of finite and finite irreducible and affine irreducible, so the ones that are infinite, are all classified. Okay, and this can be shown for AN tilde through Cox-Moody algebras, but for the finite ones, I implore you to go through Ardila's lectures and see that all the finite ones can be constructed, and it'll be different than AN tilde, because AN tilde, you'll find out you can't really construct like a bijection between these two, right? Because all these are going to have some, even you can see it here, right? Right, everyone is going to have some neighboring pair, in which is going to be order 3, whereas like this one and this one don't really have, right, a neighboring pair.
Yeah,
it's not degree 2 at the end here, right? And you can't.
Yeah, I definitely see the difference.
Yeah.
Thanks.
Yeah, but if you need go through Bourbaki, or Cox-Moody, I think Cox would have.
I'd rather see
affine.
an Ardila lecture than go through Bourbaki, but
Yeah, but I guess Ardila has a nice combinatorial proof of the finite ones. So if you need to go through that, it's in his Coxeter group lectures, and you can go through that as well. But for the affine ones, Cox-Moody would probably have it.
great, thanks.
Yeah.
Any other questions? All right. In that case, we'll thank Brandon once again. Thank you, Brandon.
Thanks.
Very nice.